Hi, welcome back. In this lecture, I would like to talk about encoding methods for expressing matrices using quantum states. We will see that there are two main techniques. The first one is amplitude encoding. It's very similar to the vector amplitude encoding we saw in the previous lecture. But the most interesting one is the so-called quantum simulation approach or quantum simulation encoding, where we are going to use quantum gates and operators to express the matrices entries. So let's start with the first encoding. So the most obvious way of encoding an m times n matrix of values would be to employ m QPU register. So if we have m rows in our matrices, we are going to have m QPU register. Each of these QPU registers is a length of log base 2 of n to amplitude encode each row of the matrix as it were a vector. On the right of these slides, you can see, for instance, an example. In this case, we're going to have m rows, and we can see the first 3 rows here. So for each row, we use one quantum register. So row 1, we use quantum register 1, row 2, quantum register 2, and row 3, we're going to use a quantum register 3. For each of these rows, we're going to use an amplitude encode to express the values of the matrix. So this is very similar to what we saw in the previous lecture. However, we're going to use a different quantum register to express different rows of our matrix. So in this case, the number of rows is equal to the numbers of a quantum register that we're going to use. So what is the issue with this? Well, the issue is really that it's going to be difficult to express operation on using this matrix. Right? So this formulation does not necessarily represent the data as a matrix very well. So for instance, we're going to have trouble whenever we want to do a transpose of this matrix, or we want to do a matrix multiply using the values of the matrix encoded in amplitude encoding. So to address this issue, people introduce another technique, another formulation, another encoding called quantum simulation encoding. I want to go with you through the basic ideas of the quantum simulation encoding, and then the next lecture we're going to go more into detail. So one thing that we saw during the quantum phase estimation primitives was that a QP operation is entirely characterized by its eigenstates and eigenphases. So for instance, we saw the eigenstates and the eigenphases of the Hadamard gate that is represented here. So that also means that the eigendecomposition of a matrix characterize the matrix completely. So a simpler way to convince ourselves that the QPU operation faithfully represents the data matrix is the fact that both have the same eigendecomposition. So if they have the same eigendecomposition, it will be the same matrix. So a good matrix representation is a procedure for associating a matrix. So we have a certain matrix with a QP operation that can be efficiently implemented to single and multi-qubit operation. So the quantum simulation approach is basically associating a certain matrix to a number of QPU operation, a number of QPU gates. So for certain matrices classes, the quantum simulation procedure provides a very good matrix representation that allow us to perform operation like transpose and matrix multiplication. Quantum simulation encoding is a term for a whole class of procedures that can find efficiently implementable QPU operation for representing Hermitian matrices. So we said that they're good for a certain class of matrices. This class is the Hermitian. As desired, quantum simulation techniques provide a QPU operation having the same eigendecomposition as the original Hermitian matrices. So in summary, this quantum simulation encoding is associating Hermitian matrix with a number of QPU gates, a QPU operation that we can implement using our QPU instruction. And this gate will represent our This composition of gain will represent our matrix. So this is the last slides of this lecture. In the last lecture, we're going to go more in detail on the quantum simulation approach. Talk to you soon.